Welcome to the deep dive. Today, we're diving straight into large language models, or LLMs. You've likely seen the buzz around them, especially since ChatGPT arrived back in November 2022.
Absolutely. These LLMs have, well, they've really exploded onto the scene, haven't they? Their ability to understand and generate human-like language is pretty impressive.
It really is, and that comes from training these massive neural networks.
Exactly. We're talking billions of parameters trained on just enormous data sets of text. The general idea, has been that bigger often means better, following these scaling laws.
Billions of parameters and massive data sets. Yeah, it's a lot to wrap your head around. And keeping up with everything feels like, well, a full-time job almost.
Oh, definitely. New models, new techniques pop up constantly. It's moving incredibly fast.
So that's kind of the goal here today, right? To cut through some of that noise.
Precisely. We want to give a clear, accessible overview of where things stand with LLMs based on a really thorough survey paper that maps out the recent advancements.
Okay, consider this our guide to the LLM jungle. Now, this didn't just happen overnight, did it? There's a history here.
No, not at all. LLMs stand on the shoulders of decades of research. The survey mentions four main waves. First, statistical language models, then neural language models,
Right.
then pre-trained language models, which really set the stage, and now finally these large language models.
So, for clarity, how are we defining an LLM today?
Fundamentally, you can think of them as large-scale, pre-trained statistical language models that are built using neural networks. It's that combination, the scale, the pre-training, the architecture that gives them their power.
Got it. Large-scale, pre-trained neural networks. Okay, so the survey starts by looking back at some of the early pre-trained neural language models. Why start there?
Because they really laid the foundation. The core concepts, the architectures developed back then, they're still fundamental to how today's LLMs work, essential building blocks.
And a huge piece of that puzzle was the transformer architecture, wasn't it, from that 2017 paper?
Oh, absolutely. The transformer was revolutionary. Its self-attention mechanism was the key thing.
Self-attention, allowing it to look at all the words at once.
Exactly. Unlike older models that processed words one by one, transformers could weigh the importance of all words simultaneously. This parallel processing, especially with GPUs, just unlocked the ability to train much, much bigger models efficiently.
And these early models, the PaLMs, they weren't built for one specific job initially.
Correct. They were designed to be task agnostic. You pre-train them on a ton of unlabeled text
Hmm.
to learn general language patterns,
Hmm.
and then you fine-tune them on smaller, specific data sets for whatever task you need.
Okay, so we've got PaLMs, transformers. The survey then breaks down PaLMs into types, starting with encoder-only models. What's their main characteristic?
Encoder-only models are all about understanding the input context. Their attention mechanism can look at the entire sentence, both forwards and backwards, to understand each word, bidirectional context.
And how do you train them to do that?
Often by corrupting the input somehow, like masking out words and forcing the model to predict what was masked based on the surrounding context.
Makes sense. So if they're good at understanding the whole sequence.
They excel at tasks like text classification, sentiment analysis, or question answering, where you need that full context.
And the big name here is BERT, right? Bidirectional encoder representations from transformers.
Definitely. BERT was a landmark model. The embedding layer, the stack of transformer encoders, and a final layer for output.
And it used those two pre-training tasks, masked language modeling, which you mentioned, and next sentence prediction. Why those two?
Well, masked language modeling teaches deep contextual understanding. Next sentence prediction aimed to teach relationships between sentences. The idea was, if a model masters these, it gains a broad language understanding useful for many other tasks.
And BERT really kicked off a wave of similar models, didn't it?
It absolutely did. You saw Roberta, which tweaked the training for more robustness. Albert focused on reducing parameters for efficiency. Deberta improved the attention mechanism.
Huh?
And Electra used a clever replaced token detection task.
Replace token detection. How did that help efficiency?
Instead of just masking, Electra replaced some words with plausible fakes from a smaller generator model. Then the main model acted like a discriminator, trying to spot the fakes.
Okay.
It's more efficient because the model makes a prediction for every token, not just the masked ones, so it learns faster from the same amount of data.
Clever. The survey also mentions cross-lingual models like XLMs. What's the challenge there?
Getting the model to understand connections between different languages. XLMs use techniques like shared vocabularies and specific training objectives to align representations across languages.
And some encoder models like XLNet and UNLM borrowed ideas from decoders.
Right. XLNet used a permutation-based approach to learn bidirectional context in an auto-aggressive way. UNIM unified training for both understanding and generation tasks using clever masking strategies.
Okay, that covers encoder-only models well. Let's switch to decoder-only PLMs. Their strength is generation.
Primarily, yes. They're built to predict the next word in a sequence, given the words that came before, autoregressive generation.
And GPT-1 was the first big success story using this approach.
Yes, GPT-1 really showed that generative pre-training followed by task-specific fine-tuning could work incredibly well across many different NLP tasks.
Then GPT-2 came along, trained on that huge web text dataset, and showed it could do tasks without fine-tuning, just from the prompt. That was pretty mind-blowing.
It was. GPT-2 is basically a scaled-up GPT-1 with a few architectural tweaks, layer arm placement, bigger vocabulary, longer context. But the scale, trained on that diverse web data, unlocked impressive zero-shot capabilities. It could just infer the task from the prompt.
Incredible. Okay, third category, encoder-decoder PLMs, sequence-to-sequence tasks.
Exactly. Things like machine translation or summarization, where you map an input sequence to a different output sequence. They have distinct encoder and decoder components.
The survey lists T5, BART, and others. What was BART's approach?
BART used a denoising objective. It would corrupt text in various ways, masking spans, deleting text, shuffling sentences, and then train the model to reconstruct the original clean text. This turned out to be a very effective pre-training strategy for sequence-to-sequence tasks.
Okay, so those are the foundational PLM architectures. Now we get to the main event. The truly large language models, GPT, LLaMA, PaLM. What's the big leap here?
Scale, fundamentally. Orders of magnitude, more parameters, tens, hundreds of billions, trillions of tokens in training data. And this scale doesn't just improve performance, it leads to these emergent abilities.
Emergent abilities, like skills that just appear at a certain size?
Kind of, yeah. Capabilities like complex reasoning or few-shot learning that aren't really seen in smaller models seem to emerge once you cross a certain threshold of scale and data. It's fascinating.
It really is. Let's start with the GPT family from OpenAI. Decoder only, right?
Yes, consistently decoder-only transformers. We mentioned GPT-1 and 2. Then GPT-3 arrived with, I think, 175 billion parameters in its largest version. Huge leap.
And GPT-3 really nailed that in-context learning, didn't it? Where you just show it a few examples in the prompt. Figure 9 in the survey shows how bigger models use that better.
Exactly. That was a major finding. Scale itself enables learning from examples within the prompt. After GPT-3 came Instruct GPT.
Right, the one focused on alignment using RLHF, reinforcement learning from human feedback.
Precisely. This was crucial. Making models not just powerful, but also helpful, honest, and harmless. Aligning them with user intent.
How does RLHF work, roughly? Figure 10 gives a picture.
It's a multi-step process. First, collect human demonstrations of desired behavior, fine-tune a model on that.
Right.
Then collect human comparisons ranking different model outputs for the same prompt. Use those rankings to train a reward model that learns to predict human preferences. Finally, use that reward model in reinforcement learning to fine-tune the language model again, optimizing it to generate outputs that humans would likely prefer.
That's quite involved, but makes sense to steer the model better. And the GPT line includes specialized models too, like Codex.
Yes, Codex was fine-tuned specifically on code, powering GitHub Copilot. Showed amazing code generation ability. And WebGPT was trained to use a web browser to answer questions.
And then, of course, ChatGPT and GPT-4. Figure 11 showing GPT-4 acing exams is pretty striking.
GPT-4 was another big step up. Better reasoning, handling images as well as text, and just top-tier performance on many benchmarks, sometimes exceeding human scores.
Okay, moving to the LLaMA family from Meta. What's their defining feature?
Openness, largely. Meta released the weights for LLaMA models, initially under a non-commercial license, allowing the research community to build on them. That really spurred innovation.
Right, fostering that open ecosystem. The first LLaMA models came out in early 2023.
Yes, ranging from 7 billion to 65 billion parameters, trained on trillions of tokens. Architecturally similar to GPT-3, but with some tweaks like SWID-GLU activations and rotary embeddings.
And notably, the smaller LLaMA models were competitive with much larger ones like GPT-3.
Exactly. LLaMA 13b performed comparably to GPT-3 175b on many benchmarks, suggesting that data quality and architectural choices are also really important, not just raw parameter count.
Then came LLaMA 2 with Microsoft, including chat versions. Figure 12 shows its training involved RLHF too.
Yes, LLaMA 2 Chat followed a similar path. Supervised fine-tuning on dialogue data first, Then iterative refinement, using RLHF employing techniques like rejection sampling and PPO to better align with conversational expectations.
And the llama family tree just exploded, right? Koala, Mistral 7B, Code Llama, Figure 8 shows a lot of branches.
It really did. Koala learned from interaction data. Mistral 7B is remarkable for punching way above its weight class in terms of performance versus size. Code Llama is for code. Then you have Gorilla for API calls, Giraffe for long context, and many others. It shows the power of open models.
Definitely. Okay, third major family, PaLM from Google. Their first one was also huge.
Yep. PaLM-1 clocked in at 540 billion parameters. Trained efficiently using Google's pathway system, it showed really strong few-shot learning and reasoning capabilities.
And they had uPaLM and this UL2R thing for continued training.
Right. uPaLM essentially kept training PaLM using UL2R, a mix of denoiser's objective. This offered computational savings while still improving the model cheaper than training a whole new one from scratch.
Then Flan PaLM, that was all about instruction tuning, right?
Mm.
Figure 14 shows a ton of task types.
Exactly. Flan PaLM fine-tuned uPaLM on something like 1,800 diverse tasks described via instructions, including chain of thought data. This massively boosted its ability to follow instructions and generalize to new tasks. Instruction tuning proved very powerful.
And the successor PaLM 2 aims for better efficiency and multilingual reasoning skills.
Correct. PaLM 2 is designed to be more compute efficient while improving on PaLM across various sizes and capabilities. They also developed specialized versions like MedPaLM for the medical domain.
So GPT, LLaMA, PaLM are the big three. But the survey highlights many other important LLMs.
Oh yeah, tons.
Yeah.
LFAN, which really pioneered instruction tuning at scale.
Mm-hmm.
Gopher, known for its systematic study of model scaling. T0, which unified NLP tasks into a prompted format.
What about models like Retro or Lambda? They seem a bit different.
Retro is interesting retrieval-enhanced transformer. It explicitly retrieves relevant text chunks from a database and conditions its generation on that retrieved info. Figure 18 shows the architecture.
Incorporating external knowledge directly.
Right, and LaMDA was Google's effort focused specifically on dialogue, fine-tuned with annotated conversations and access to external tools and knowledge for better, safer dialogue.
The list keeps going. OPT, Galactica for science, CodeGen, Alexa TM for multilingual, Minerva for math, Modal 2 with their training objectives. Yeah. It's a whirlwind. Figure 24 gives the timeline.
It really is.
Yeah.
GLM 130B, Pythia, Orca imitating bigger models, StarCoder for code, Gemini for multimodality, plus countless others like Mamba, Mixtral, Zephyr. The pace is just relentless.
Okay, so how are these things actually built? The survey breaks down the pipeline in Figure 25. Data prep, tokenization, training, tuning, alignment.
Yep, that's the typical flow. Starts with gathering and, crucially, cleaning the data. Then tokenization breaks text into pieces the model understands. Pre-training is the big, computationally intensive step using self-supervision. Then instruction tuning and alignment fine-tune the model for usefulness and safety.
Let's touch on a few key components, architectures. We've covered encoder-only, decoder-only, encoder-decoder, all usually based on the transformer.
Mostly, yes. Transformer variants are dominant. Encoders understand, decoders generate, decoders translate or summarize.
Data cleaning sounds boring, but vital. Figure 27 shows Falcon 40B filtered out a lot of data.
Absolutely critical. Garbage in, garbage out. High-quality, diverse, deduplicated data is key. Falcon's results showed that careful data curation can really pay off.
Tokenization, breaking words into smaller bits. Byte pair encoding, word piece, sentence piece. Different ways to handle unknown words.
Essentially, yes, they are subword tokenizers. BPE merges frequent pairs. Word piece uses likelihood. Sentence piece treats spaces like characters, which helps some languages. They all aim to balance vocabulary size and handling rare words.
And positional encoding tells the model the word order. Absolute, relative, rotary, rope, alibi. Different techniques shown in Figure 28.
Right. Original transformers use absolute. Relative methods encode distance. Rotary embeddings used in LLaMA and others apply rotations. Alibi adds a bias based on distance used in Bloom. Different ways to inject sequence order info, especially important for long contexts.
Pre-training. Masked language modeling like BERT or causal language modeling like GPT. Figure 29 introduces mixture of experts. MoB. What's that?
MoE is a way to scale up models efficiently. Instead of one huge, dense network, you have many smaller expert networks, and a router directs parts of the input to specific experts.
So only some parts of the model are active for any given input.
Exactly. It allows for models with a massive total number of parameters, but the compute cost during inference is much lower because it's sparse activation. Models like Mixtral and potentially GPT-4 use this.
And fine-tuning versus instruction tuning, what's the core difference?
General fine-tuning adapts a pre-trained model to one specific task, like sentiment. Instruction tuning fine-tunes on a collection of tasks described via instructions, aiming for better generalization and instruction following ability. Self-instruct even uses the model itself to generate more instruction data.
Alignment is crucial for safety. We mentioned RLHF. Figure 30 shows direct preference optimization. DPO, what's that about?
RLHF uses human feedback to train a separate reward model. RLAIF uses AI feedback. DPO is a newer method that tries to achieve alignment more directly from preference data without needing the separate reward model step or complex reinforcement learning, potentially simpler and more stable.
Okay, and finally, decoding strategy is how the model actually picks the words to output. Greedy, beam search, top K, top deck sampling.
Different ways to navigate the probability distribution the model produces. Greedy takes the most likely word. Beam search explores multiple paths. Sampling, top K, top nucleus, adds randomness for more diverse or creative output, controlled by temperature.
Wow, that's a deep dive into the mechanics. Okay, so how are these models used and how do we enhance them? Figure 36 gives an overview. Simple prompting isn't always enough.
Right, basic comps work, but for complex tasks or to overcome limitations like knowledge cutoffs or hallucinations, you need better prompting strategies or ways to augment the LLM.
Let's talk about hallucinations generating plausible but incorrect or nonsensical stuff. Intrinsic versus extrinsic.
Intrinsic hallucinations contradict the source information you might have given the model. Extrinsic ones are things it makes up that aren't in the source but don't directly contradict it, either harder to spot sometimes.
And tackling hallucinations is a big driver for better prompt engineering.
Definitely. Crafting good prompts is key. Beyond simple instructions, techniques like chain of thought, CUT, make a big difference.
QT getting the model to think step by step.
Exactly. You either explicitly ask it to, zero-shot code T, or provide examples of step-by-step reasoning, manual show. It really helps with complex reasoning tasks.
And there are more advanced versions like tree of thought or reflection.
Yes, tree of thought explores multiple reasoning paths simultaneously. Reflection involves letting the model critique its own output and refine it, trying to make the reasoning process more robust.
Expert prompting, getting it to act like an expert.
Yeah, tell it, you are a physics expert. A multi-expert approach might ask for perspectives from several simulated experts.
Chains and rails.
Chains link multiple prompts together, output of one feeds the next for multi-step tasks. Rails are like guardrails to keep the output within certain bounds, topical, factual, safe. And automatic prompt engineering tries to find the best prompts automatically.
Okay, besides better prompts, we can augment LLMs with external knowledge using ARG retrieval augmented generation. Figures 37 and 38 show this.
Exactly. ARGI is huge. Before generating, the system retrieves relevant documents or data snippets from an external source based on the query.
Like a quick lookup.
Yeah. That retrieved info is added to the prompt, giving the LLM up-to-date, relevant context to ground its answer. It addresses the static knowledge problem. Flare is a more advanced version that decides when and what to retrieve during generation.
LLMs can also use external tools, right? Like calculators or search engines, Toolformer, Gorilla.
Absolutely. This extends their capabilities beyond text. They can learn to call APIs, run code, access databases. Toolformer showed models can learn when to use tools. Gorilla focused on reliable API usage. ART is a prompting technique combining reasoning and tool use.
And this leads to LLM agents models acting more autonomously. Figures 39 and 40 touch on this.
Yes, agents use the LLM as a reasoning engine to plan and execute steps to achieve a goal. Techniques like React, Reason and Act, or DRA combine reasoning with taking actions, using tools, maybe even asking clarifying questions. It's moving towards more independent problem solving.
Fascinating stuff. Of course, none of this works without data for training, tuning, and evaluation. The survey covers popular data sets, categorizing them by capability in Figure 41.
Crucial. You need benchmarks. There are data sets for basic tasks, natural questions, MMLU for general knowledge, MBPP and Human Evil for code, HELLA-SWAG for common sense, Squad for reading comprehension. Table 2 lists many.
And data sets specifically for those emergent abilities, reasoning, instruction following.
Right. GSM-8K for grade school math problems, math for harder math, ARC for reasoning challenges, Truthful QA for honesty, OPT-IML bench for instruction learning itself.
And for the augmented abilities using knowledge or tools.
Datasets like Hotpot QA require finding info across multiple documents. Tool QA tests tool used directly. GPT-4 Tools provides data to train models to use tools.
So with all these models and data sets, how do they actually stack up? The survey presents performance comparisons, but cautions against declaring a single best model.
That's right. Performance varies hugely by task, metric, prompt style. It's complex. The survey categorizes models, size, type, origin, availability in Table 3, Figure 43, and shows performance snapshots in Tables V to X.
Right, we see tables for common sense, hella swag, symbolic reasoning, world knowledge, WikiFact, coding, human eval, arithmetic, GSM-8K, even hallucination, halu eval.
Exactly. They give a sense of relative performance on specific benchmarks, but it's just a partial picture. And comparing results across different papers can be tricky due to different evaluation setups.
Understood. So looking ahead, what are the big challenges in future directions?
Well, a major one is efficiency, the need for smaller, faster, cheaper models. PEFT methods like LoRa and knowledge distillation are key here.
And the survey asks if the transformer is the end-all be-all, mentions post-attention architectures like RWKV, Hyena, figures 32, 33 compare complexities.
Right. Transformers are great, but have quadratic complexity with sequence length. Researchers are exploring alternatives that might scale better for very long contexts, offering linear or near-linear complexity. It's an active research area.
Multimodal models are another big one, Gemini integrating images, audio.
Definitely. Moving beyond just text to understand and reason across different data types is a major frontier. Aligning vision and language is key.
And we'll keep seeing better ways to use and augment LLMs. Better prompting, RG, tools, agents. Dealing with longer contexts seems important too.
For sure. Improving these interaction and augmentation methods is ongoing. Context length is a persistent bottleneck, so finding efficient ways to handle more information is critical. And MOEs, mixture of experts, are becoming more common in frontier models, bringing their own set of opportunities and challenges for training and inference.
Plus, the ever-present concerns around security, ethics, bias, truthfulness, responsible AI development.
Absolutely paramount. Ensuring these powerful tools are used safely and beneficially is a huge ongoing challenge for the entire field.
This has been an incredibly thorough deep dive. We've really covered the landscape of large language models, from their roots to the current state of the art and where things might be headed.
Indeed. It's a field defined by rapid progress and, well, a lot of complexity. We've touched on architectures, data, training, usage, evaluation. It's multifaceted.
And that point about evaluation being tricky is worth remembering. No single best model. It really depends on the job.
Exactly. What works best depends entirely on the specific application, the metrics you care about, and how you interact with the model. The landscape is constantly shifting.
It truly is dynamic. So for everyone listening, maybe think about which part of this evolution resonates most with you. Is it the push for efficiency, the integration of multimodality, the development of more autonomous agents, or maybe the fundamental challenges of alignment and safety?
It's a field with huge potential and significant hurdles still ahead. Understanding its different facets is key to navigating its future.
A future that's unfolding right now. Thanks for joining us for this deep dive.